All right, hello and welcome. Have you ever just looked around and wondered what everything is actually made of, like really made of? Well, you're in exactly the right place. Today, we're diving deep into one of the most fundamental topics in all of chemistry, the structure of the atom. Let's get right into it. So, why should you care about the structure of the atom? I mean, really? What's the big deal? Well, this quote right here, it says it all. Everything. And I mean everything. From why salt dissolves in water to why carbon is the backbone of life, it all boils down to what's going on inside these tiny little things called atoms. If you can understand the atom, you unlock the secrets to pretty much all of chemistry. So here's our game plan for this explainer. We're going to start at the very beginning with the first ideas about the atom. Then we'll watch a revolution unfold with the discovery of the nucleus. After that, we'll take a huge leap with Niels Bohr into the quantum world. From there, we'll explore the modern model, which is where things get really weird. And finally, we'll put it all together and actually build some atoms and solve a couple of classic problems you might see on an exam. Okay, first up, the atom's debut. Let's jump in our time machine and head back to the 19th century. This is where the atom goes from just a cool philosophical idea to something scientists could actually study. You can think of this as chapter one of an epic scientific detective story. The first big clue came way back in 1808 from a guy named John Dalton. He proposed that everything was made of these tiny, indivisible balls called atoms. And for almost 100 years, that was the main idea. But then, in 1897, J.J. Thomson did some experiments that completely changed the game, leading to his famous plum pudding model just a few years later. So, here's the big shift in thinking. Dalton's view was simple. The atom is the end of the line. You can't cut it into smaller pieces. But then came new evidence from these things called cathode ray tubes. Think of them as old-school TV tubes. By zapping gas with electricity, scientists saw that little, negatively charged bits were being knocked out of the atoms. Suddenly, the indivisible had been divided. And that little particle was given a name you definitely know, the electron. This was a huge deal. It was the very first subatomic particle ever discovered. Its existence proved that the atom wasn't just a simple solid ball. Nope, there was something more complex going on inside. So to explain this new discovery, Thomson came up with what we call the plum pudding model. Just picture a ball of positively charged dough, or pudding, and stuck inside it, all scattered around, are the little negative electrons, like plums or raisins. You can also think of it as a watermelon, where the red part is the positive charge and the seeds are the electrons. It was a pretty good first guess, and it correctly showed that the atom was neutral overall. But as you'll see, this model's days were numbered. And this is where the plot really thickens. Because it was one of J.J. Thomson's own students, a brilliant physicist named Ernest Rutherford, who designed an experiment that didn't just poke holes in the plum pudding model, it completely blew it to pieces. Now, the setup itself sounds almost ridiculously simple. Rutherford took a source that shoots out these tiny positive particles, called alpha particles, and he fired them at a sheet of gold foil that was unbelievably thin. Then he put a special screen around it that would light up with a little flash every time a particle hit it. Simple, right? But the results were anything but. Okay, so this is where things get wild. If the plum pudding model was correct, all those alpha particles should have just blasted right through the gold foil, like a bullet through a fog bank. And yeah, most of them did, but that's not the whole story. Some of them were deflected at an angle. And this is the part that blew everyone's minds. A tiny, tiny fraction, about 1 in every 20,000, ricocheted almost straight back. Rutherford himself couldn't believe it. He said it was like firing a cannonball at a piece of tissue paper and having it bounce back and hit you. It was completely impossible, according to the science of the day. It meant the plum pudding model had to be totally wrong. And this is just perfect science in action. The prediction failed, so it was time for a new conclusion. Rutherford realized that for a positive particle to bounce back like that, it must have hit something incredibly small, incredibly dense, and also positively charged. This led him to a revolutionary new idea. The atom is mostly empty space with a tiny, heavy positive center. And that tiny core got a name, the nucleus. This is where almost all the mass of the atom is packed, and it's where all the positive charge is. The little negative electrons, he figured, must be orbiting this nucleus, kind of like planets zipping around the sun. Now, this nuclear model was a huge step forward, a massive leap. But it wasn't perfect. In fact, according to the physics of the time, it had some pretty major problems. So, what exactly was wrong with this new solar system atom? Well, there were two killer flaws. First, basic physics said that an electron orbiting like that should constantly be giving off energy. This would make it slow down and spiral into the nucleus in a fraction of a second, causing the atom to collapse. But obviously, atoms are stable. The second problem was that it couldn't explain why different elements glow with very specific, unique colors when you heat them up, like a neon sign. This is called their line spectrum, and it's like a unique barcode of light for each element. Rutherford's model had no answer for it. So, to fix these problems, science needed another hero, another revolution, and it came from the Danish physicist Niels Bohr. He did something incredibly brave. He suggested that maybe, just maybe, the normal rules of physics simply don't apply inside an atom. He brought in a brand new, radical idea called the quantum. So here's the absolute heart of Bohr's model. He basically just threw out the old rulebook. He said, forget that spiraling to death thing. Electrons can only exist in special fixed orbits, kind of like planets stuck on specific tracks. Each track or orbit has a fixed amount of energy. As long as an electron stays on its track, it doesn't lose any energy. Boom! Stability problem solved. And he said an atom only gives off light when an electron jumps from a high-energy track to a low-energy one. Boom! Line spectrum problem solved. And what a success it was. Bohr's model was brilliant. It perfectly predicted the line spectrum for the simplest atom, hydrogen, and it finally explained why atoms don't just instantly collapse. It was this amazing mix of old-school planetary ideas and brand-new quantum rules. But you know how science works, right? It never stops asking questions. And while Bohr's model was a masterpiece for hydrogen, it didn't work for more complicated atoms. And there were other weird things it couldn't explain. The atomic story, it turns out, was about to get a whole lot weirder. And now we arrive at the modern view of the atom. To really get this next part, you kind of have to take everything you know about how the world works, with solid objects and predictable paths, and just set it aside. We're diving headfirst into quantum mechanics, where things get strange. This one question, is the key to understanding the modern atom. For this whole story, we've been picturing the electron as a tiny little ball, a particle. But what if it's not just a particle? What if it's something more? So in 1924, a physicist named Louis de Broglie asked this incredible question. He knew that light, which we normally think of as a wave, can sometimes act like a particle. So he thought, well, could it work the other way around? Could a particle, like an electron, sometimes act like a wave? And it turns out the answer is yes. This idea, wave-particle duality, is a cornerstone of modern physics. An electron isn't just a point, it's also a spread-out wave. And if that wasn't weird enough, right after de Broglie comes Werner Heisenberg with his uncertainty principle. And this is a mind-bender. It basically says that there's a fundamental limit to what we can ever know about a particle. The more precisely you measure an electron's position, where it is, the less precisely you can know its momentum, where it's going, and vice versa. You can literally never know both perfectly at the same time. So what does all this weirdness, electrons as waves, the uncertainty principle, mean for our picture of the atom? Well, it means Bohr's neat, clean, predictable orbits have to go. They're impossible. If an electron is a wave and you can never know its exact path, then you can't have an orbit. Instead, all we can talk about is the probability of finding an electron in a certain region of space, and we call these fuzzy 3D regions of high probability orbitals. Now, to describe these orbitals and the electrons in them, we use a set of 4 quantum numbers. The easiest way to think about this is like an electron's complete mailing address. The first number, n, is the principal quantum number. That's like the city, telling you the main energy level. The second, L, is the azimuthal. That's the street, describing the orbital's shape. The third, m sub L, is the magnetic. That's the house number, specifying its orientation in 3D space. And finally, m sub S, the spin, tells you about the electron itself. Let's just say it's like the person living in the house, and they can be either spin up or spin down. Okay, so we've got this incredibly powerful, but admittedly strange new model of the atom. That's great, but how do we actually use it? Well, now we're going to look at the rules for how electrons actually fill up these orbitals to build all the different atoms in the universe. This is where the theory gets super practical, especially when it comes to exams. So there are three main rules to this game. First is the Aufbau principle, which basically says electrons are lazy. They always go into the lowest energy orbital available first. Second, the Pauli exclusion principle. This says that no two electrons in an atom can have the exact same four-part quantum address. A practical consequence of this is that any single orbital can only hold a maximum of two electrons, and they have to have opposite spins. And finally, there's Hund's rule. Think of it this way. When you have multiple orbitals of the same energy, electrons prefer to get their own room before they're forced to pair up. Now, a really important consequence of these rules, and something you absolutely need to know, is that atoms get a special bonus of stability when their subshells are either exactly half full or completely full. You can kind of think of it like a perfectly balanced tire. It's just more stable that way. This extra stability comes from the beautiful symmetry of the electron arrangement. All right, enough theory. Let's get our hands dirty and solve a typical problem you might run into. Here we go. We need to calculate the wave number of some yellow light that has a wavelength of 5,800 angstroms. So how would you go about tackling this one? Let's walk through it together. Step 1, you need the right formula. And for this, it's super simple. Wave number is just 1 divided by the wavelength. Now, step 2, and this is where people often mess up, you have to convert the units. The formula needs the wavelength in meters, but we're given it in angstroms, so we just multiply by 10 to the minus 10. Finally, step 3 is just plugging it into your calculator. 1 divided by our new number in meters gives us the final answer, 1.724 times 10 to the power of 6 per meter. Easy. Okay, ready for another one? This one's a bit more of a puzzle, and it really tests your understanding of the basic makeup of the nucleus. We're told an element has a mass number of 81, and we have a clue about its neutrons and protons. The goal is to figure out what element it is. Let's break this one down. First, we need to turn the words into math. We know protons plus neutrons equals the mass number, so that's our first equation. P plus N equals 81. We're also told that neutrons are 31.7% more than protons. That means N is equal to 1.317 times P. Now we just substitute the second equation into the first one. That gives us P plus 1.317 P equals 81. A little bit of algebra later, and we find that P, the number of protons, is 35. And since the number of protons is what defines an element, we just look at our periodic table, find element 35, and it's bromine! So the final symbol is bromine-81. And that, believe it or not, brings our whole journey to a close. We've gone from Dalton's simple little sphere all the way to the weird, fuzzy, probabilistic clouds of quantum mechanics. We've covered a ton of ground. And just remember, this chapter is so important. It's an absolutely essential topic, and mastering these concepts is going to pay off big time in your studies and on your exams. But before you go, I want to leave you with one final thought to chew on. That uncertainty principle, it isn't just a weird rule for tiny particles. It's a statement about the fundamental nature of the universe. So if we can never ever know everything about even a single simple electron, what does that say about the limits of human knowledge? And what does it tell us about the nature of reality itself? It's a question that takes us way beyond chemistry and right into the heart of philosophy. Something to think about. Thanks for joining me.